So we just learned how to count atoms by weighing. Now we're going to talk about counting molecules. So for an element, the molar mass is the mass of 1 mole of atoms. For compounds, the molar mass is the mass of 1 mole of molecules or formula units of that compound. So why does it have to be molecules or formula units? Well, ionic compounds don't have molecules. They are just alternating arrays of positive and negative ions. The formula for an ionic compound just gives us the lowest ratio of each kind of atom. So there's not an actual molecule. So we call those formula units. It's a slight distinction that I just don't want to confuse you. So, just trying to be completely correct, it often says molecules or formula units. So we can convert between the mass of a compound and the moles of a compound, and then we can calculate the number of molecules or formula units from the number of moles. It's the same process that we did. The only difference is instead of just looking up the molar mass in the periodic table, we have to actually calculate it. So what's the molar mass of a compound? It is the same number as the formula mass, but a different unit. So the formula mass, you look at how many atoms of each element are in the formula, you add up their masses in atomic mass units, you get a number. The unit is atomic mass units. The mass of 1 mole of molecules or formula units is the same number in grams. So let's calculate the formula mass of calcium nitrate. So we have 1 calcium atom. How many nitrogen atoms? 2. And how many oxygen atoms? 6. So we need these values off the periodic table. So calcium was 40.08. So 1 times 40.08 atomic mass units. And 2 nitrogens, 2 times the atomic mass of nitrogen, plus 6 atoms of oxygen. Each atom of oxygen weighs 16 atomic mass units. And I'm coming up with 164.1. Anybody else get that? So 1 formula unit, 1 formula of calcium nitrate weighs 164.1 atomic mass units. 1 calcium atom, 2 nitrogen atoms, 6 oxygen atoms. What's the molar mass of calcium nitrate? What if we had a mole of calcium nitrate units? It's the same number, but change the unit to gram. Because you have 1 mole of calcium, 40.08 grams. Here, I'll write it out. So 1 mole of calcium atoms times 40.08 grams per mole of calcium. And we have 2 moles of nitrogen times 14.01 grams per mole of nitrogen. And 6 moles of oxygen times 16.00 grams per mole of oxygen. And that comes out to be 164.1 grams. Same process. Any questions? So find the number of moles in a 22.5 gram sample of dry ice, which is solid CO2. So the number, 22.5 grams, and the unit that we're trying to find is moles. So we're going from grams to moles. Grams to moles is the relationship 1 mole is Avogadro's number of things. So that's always just a single step. So 22.5 grams times and a fraction. Moles on the top, grams on the bottom. And so we've got the units to work out. Then we need this relationship between moles and grams. That's the molar mass. For an atom, you just look it up in the periodic table. For a compound, you have to calculate it. Here's our formula, CO2. So on the bottom here, I'm looking at CO2. And so I look at how many atoms of each element. I've got one carbon, and I'm going to put in how much does 1 mole of carbon weigh? 12.01 grams. And I have 2 moles of oxygen. How much does each mole of oxygen weigh? 16.00 grams. And I believe that comes out to 44.01. Is that correct? So that is the mass of 1 mole. So that many grams is equal to 1 mole of CO2. So that's the conversion factor I need. 1 mole of CO2 weighs 44.01 grams. So I've got 22.5 divided by 44.01. I should have 3 significant figures, 0.511, write down 2 extras, and the unit is moles. And then when I round that, the number that I'm getting rid of, the first one there, the 2, is less than 5, so I can round down, 0.511 moles. Any questions? This type of calculation is really, really important in chemistry. Let's do another one. Calculate the number of moles of NO2 in 1.18 grams of NO2. Pull out the number that's given, 1.18 grams. You don't have to write the formula for the compound, but it doesn't hurt either. So that's what I'm given. I'm given grams. They're asking me for moles. Grams to moles is 1 step. So 1.18 grams of NO2. And I'm going to have 1 fraction here. Moles on top, grams on the bottom. The relationship between grams and moles is the molar mass. I would encourage you strongly to show how you calculate this because it's very easy to make mistakes. If you've written it down, then you can see what happened. So down here, NO2. I like to write the formula just so that I don't have to look around for it. So I've got 1 mole of nitrogen, 14.01 grams. And there's 2 moles of oxygen in there. Each mole of oxygen is 16 grams. So I've got 14.01 plus 2 times 16, 46.01 grams. That is equal to 1 mole of NO2. So this molar mass is a conversion factor. It's going to be different for different compounds. And it's not just like given anywhere because there's about 3 kajillion different compounds. And so, you know, there are books that list them all, but they're not very useful. It's better to just have the periodic table and calculate it. So 1 mole, 46.01 grams. 1 mole weighs 46.01 grams. So I have 1.18 times 1 divided by 46.01. I should have 3 sig figs in my answer. The zeros don't count at the beginning. 2, 5, 6, there's my third sig fig. I'm going to write down 2 extras, 4, 7, and the unit will be moles. And then when I round that, I get 0.0256 moles. Any questions? So I want to talk to you about scientific notation for a minute, because as I was grading lab reports over the weekend, some of you are doing some pretty crazy things. I've seen them before. Other people have had those same crazy ideas. But I want to get that straightened out. So do I have to report this in scientific notation? No. It does not say calculate the number of moles, express your answer in scientific notation. If it specifically says that, then yeah, you better do it. My rule of thumb is if there's zeros at the beginning or zeros at the end, if you have to get your finger out to count them, use scientific notation. If there's, 2 or 3 zeros, usually we can just see 3 zeros and we don't have to count. But beyond that, it gets a little iffy. So this is fine. If we want to put this in scientific notation, some of you are doing some crazy things. You're starting from the end of the number and counting how many decimal places you need to move it. Okay, that's not going to work, because then it depends on how many display places your calculator has. Because if I wrote it like this, I'd end up with one number, but my calculator actually goes on. It has 4, 6, 5, 9, 9. So what if I had a calculator with more digits? Well, then you'd have more digits. We're not doing anything with the end of the number. We're looking at where the decimal point is here, and to put it in scientific notation, it goes after the first non-zero digit. Not the second or third, the first one. So as we're going left to right, what's the first non-zero digit? 0, 0, 2. The first digit you come to that's not a 0. That's where you're going to put the decimal point. So I want the decimal point to go there. So it's going to be 2.56. I'm going to stop because that's my sig fig, my last significant figure, and then it's times 10 to the something. I'm going to count from where the decimal point was originally to where I ended up putting it. So I moved it 1, 2 places. So the exponent is 2. And then I ask myself, positive or negative? Well, is this a big number or a small number? 0.02, that's a small number. Mrs. K has negative feelings about small paychecks. Right? Small number, negative exponent. Okay? And then mole. So that is an equally correct answer. Any questions? So this is converting between mass and number of molecules. How many H2O molecules are in a sample of water with a mass of 3.64 grams? Read the problem, write down the number. 3.64 grams of water. And then identify what they're asking for. Asking for molecules. Okay, molecules is a big, long word. There's no accepted abbreviation for molecule. I think it's stupid. I think we should have used MOL for molecule, but they didn't. So you just have to write the whole thing out, molecules. And then we have to figure out how are we going to get from grams to molecules. We need Avogadro's number, and so let's write that down. So Avogadro's number tells us that 1 mole is equal to 6.022 times 10 to the 23rd molecules. So we could go from moles to molecules using that. How do we get from grams to moles? Molar mass. So for water, 2 hydrogens, 2 moles of hydrogen, 2 times 1.008 grams, and there's 1 oxygen, 1 mole of oxygen, 16 grams. So 1 mole of water weighs 18.016 grams. So that would enable us to go from grams to moles. Could you do this in one step? Yeah, you could. Because you can say, well, if 1 mole is this many grams and 1 mole is that many molecules, then this many molecules is equal to this many grams. So for those of you that made sense, do it in one step and you're good. I'm going to do it in 2 steps because for some people that doesn't make any sense. And those are the people I need to talk to more than the people who just kind of get it. Okay, so we're going to go with the 2 steps. So 2 arrows, 2 fractions. I look at the units in my path. Write the stupid path down. Just write it down. Grams to moles to molecules. Because now you have your own written instructions of what to do. Grams to moles to molecules. Can't spell molecules today, but there it is. This unit comes to the denominator because I want them to cancel out and go away. And then moles, I'm going to put down here, and that'll cancel out. So moles and molecules, that's the Avogadro's number 1, 6.022 times 10 to the 23rd molecules. And it's a real pain. The long number goes with the long word, and it ends up being really long. And then there's 1 mole on the bottom. Grams to moles, that's our molar mass that we just calculated right here. 1 mole is 18.016 grams. I'm underlining the 1 because that's how many significant figures the molar mass has based on the numbers I use to calculate it. And I don't want to limit the sig figs in my answer by rounding things off in here. So now I just use the calculator, 3.64, multiply by the top, divide by the bottom. So times 1 divided by 18.016 times the top, 6.022 EE23, divide by the bottom, which is 1, and I get a number. So before I write this down, I like to check and see how many sig figs should I have. Well, here I've got 4 and 4, and this is only 3. So I'm going to write down 1.21. That's my 3rd sig fig. Write down the next 2 digits times 10 to the 23rd, and the unit would be molecules. When I round that, I'm going to get 1.22 times 10 to the 23rd. Molecules. Again, there's no abbreviation for molecules. You got to write the whole stupid word. I was up too late last night. Everything seems stupid today. Sorry. Any questions? Is that a reasonable number of molecules? Yeah, molecules are crazy small. If you have an amount of any substance that's big enough to see with your eyes, 3.64 grams of water, it's not much water, but it's visible. If you can see it, it should be some ginormous number. If you end up with times 10 to the negative something, something is wrong. Either you set the problem up wrong or your calculator didn't understand what you wanted it to do. Because if you came up with even 1.2 times 10 to the negative 1, that's less than 1 molecule. Can you have less than 1 molecule? No. You either have no molecules or 1 molecule or more. Okay? Any questions?